from Virginia Polytechnic Institute and State University and DC Water District of Columbia. Welcome.
All right, good morning, everyone. We are the Virginia Tech and DC Water team. We are a multidisciplinary team consisting of data scientists, AI engineers, water specialists, and environmental engineers. Our presentation today is a solution to water treatment facility plants that could be applied across the nation. Coming from the national capital region, the size of big data that we deal with for decision support systems have been very challenging. And we believe that no decision support system will be useful or relevant without extreme security and data protection measures. And we included that major module in our system as well.
In 2018, DC Water commissioned a massive 23-foot diameter tunnel 100 feet below the river to be able to capture, convey, and store combined sewer flow that used to end up in the river. So while we've done a great job of cleaning up the river, whenever there's a rain, our plant operators are faced with a major dilemma. What is that dilemma? So as you can see, the tunnel comes in and conveys that sewer flow, combined sewer flow to our plant. And the first option is to pump it out as hard as possible and treat it through this high rate compact wet weather treatment facility system. But that requires a lot of chemicals and a lot of operator attention. But if we know that the tunnel is not going to overflow, the better option is to slowly pump it on a dry day to the main treatment plant, where through the biological means we're able to get very, very good effluent quality at the fraction of the cost. But the key is to be able to predict the level in the tunnel. And that's when we reached out to the AI team from the Virginia Tech.
Yeah, so with the increased use of sensors across most wastewater treatment facilities, and Blue Plains is one of the most advanced in the country and the world, we've been collecting data through sensors that are scattered across the entire wastewater treatment plant. The pipes, the tunnel, and the entire operations at that treatment plant. But as the size of the data is increasing, we started realizing that this data has to be protected in ways that are advanced and intelligent, which by looking at the size of the data, as the data is streaming across the different channels in the wastewater treatment plant, we realized that it could be a victim of cyber threat, cyber attacks. As you all know, there's a massive increase in cyber security incidents in wastewater treatment plants in the nation and around the world. So for any decision support system to be even dependable or reliable, it has to be protected extremely with so many different measures. With the size of data that we have, again, the only way to do that was through intelligent algorithms that are able to identify data poisoning issues and changes in the data sets that would not be identifiable otherwise. So we've developed the AI system that we're presenting today that protects the treatment plant against all types of external or even in many cases internal cyber threats. So as I mentioned, there has been a massive increase across the country. The recent case in Florida with Oldsmar's water treatment facility was a victim of a cyber security threat, and many other treatment facilities around the world.
To solve the stormwater problem as well as any potential cybersecurity threats, we succeeded to develop a system called Real-Time AI-Driven System, or RADS. RADS is an intelligent dashboard, and it has three major components. First component is a security component for identifying any potential cybersecurity threats. Second component is a prediction component that predicts the water level during any intense wet weather days. And the third one is an optimization component that can optimize the operation control along with the water flow. Now let's look at the model development process for the RADS. We collected lots of data. We are talking about big data, and these are time series sequential data set. We collected those data, we pre-processed those data, we analyzed those data to be able to feed into the model, and we tested many many AI models, including machine learning and deep learning models. And we found out that LSTM, or long short-term memory, which is a multivariate model, performs the best, and it has the most accurate and explainable result when it comes to prediction and classification. So we believe that upon deploying this model, an operator can make a decision based on the outcome of the model, and the operator can observe the explainability of the model as well during an outlier event. And LSTM performed the best because it understands the time series component of the dataset, as well as it has a memory unit that can understand the history of the dataset as well.
We developed graphs to support operators on making optimal and feasible decisions. The operator can use this dashboard to understand what is going on in the facility, and shown in the dark green line, we see what will be the water level in the tunnel for next 4 hours with a 5-minute frequency. Using this information, our optimization model calculates the best times and capacities for industrial pumps to pump the effluent from tunnel to the wet weather treatment process. Wet weather treatment process, given that it uses a lot of chemicals, is much faster but also costly. So our goal here is to minimize the amount of wastewater sent to the wet weather treatment process rather than the complete treatment process, while minimizing the risk of overflows. And to do that, we developed 3 components. If we look at the table, we can see what are the proposed times and capacities for each pump to operate. Also, after going through multiple iterations, testing, and AI assurance measures, we reached very accurate results. Our prediction model predicts what we call peak events, which are the times where the water level in the tunnel is over the half of the capacity, by 85% accuracy. And our protection model was able to detect cyber threats and what is the type of attack going on and which components are affected by these attacks by 90% accuracy, while categorizing these attacks with 70% accuracy. And finally, our RAS model was able to lower the amount of effluent sent to the wet weather treatment process by 23%.
All right, now that the model has been validated, we are getting ready to deploy this real time in our control system. So hopefully, we're hoping to have this ready, up and running by now, but maybe in the next couple weeks, next month or so, we're gonna have the real-time prediction data showing up in our control room to help our operators make a data-driven, real-time decision to help optimize the plant.
And we also developed the system in a way that's very generalizable to all other wastewater treatment facilities around the country, and that's our next goal as well. Thank you all, appreciate it.
Thank you.
Okay, thank you. And again, please hold your